Dye-sensitized solar cells (DSSC) is a solar cell made of a semiconductor coated with a dye to increase the efficiency of sunlight conversion. The performance of dye-sensitized solar cells (DSSC) is influenced by semiconductors, electrolytes, transparent conductive oxide substrates (TCO), counter electrodes, and dye sensitizers. The number of dye molecules that can be absorbed by the semiconductor is also important in improving the performance and electron injection of the SSC. The DSSC current density is influenced by the high electron injection from the photoexcited sensitizer into the conduction band of the semiconductor. The nature of the dye solution can also affect the number of dye molecules absorbed by the semiconductor. By of the properties of a solution that is easily controlled is in the concentration of the solution. The concentration of the dye solution in the semiconductor is also important to study because of its effect on performance.
Synthetic dyes such as ruthenium complex are used as sensitizers in wide bandgap semiconductors, with the efficiency of DSSC being more than 10%. The performance of DSSC-based natural sensitizers can be improved by using chlorophyll. When ethanol was used as a solvent, the DSSC efficiency increased to 36.11% compared to that achieved when distilled water was used. The acidity of the chlorophyll solution can be controlled to pH 3.5 by adding benzoic acid, which helps to increase the efficiency of the DSSC from 0.07% to 0.28%. At the time when a synthetic dye, such as ruthenium complex, is used simultaneously with an existing sensitizer within an existing wide bandgap semiconductor, the DSSC efficiency becomes over 10%. Due to the high cost, presence of heavy metals, and complex synthesis processes of synthetic dyes, natural dyes derived from leaves, fruits, and plants are a cheaper option as well as being non-toxic and fully biodegradable. The performance that belongs to DSSCS-based natural sensitizers has the ability to be enhanced through the use of chlorophyll. At the time ethanol is used simultaneously with an existing solvent, the efficiency belonging to DSSCS improved to 36.11% compared to that achieved at the same time distilled water is used. The acidity associated with chlorophyll solution can be controlled to pH 3.5 by adding benzoic acid, which helped increase the efficiency of DSSCS, which dropped by 0.07% to 0.28%. The performance of the chlorophyll-based DSSC was compared with the result obtained using the N719-based DSSC. When compared to the outcomes produced by the N719-based DSSC, the performance of the chlorophyll-based DSSC performed better.
Part 2, Material and Method. 2.1, How to make chlorophyll dye. So the first step is chlorophyll dye extracted from 100 gram papaya leaves in 1 liter ethyl alcohol. Chlorophyll dye extracted from 100 gram of papaya leaves and added into 1 liter ethyl alcohol and heated for 17 Celsius for 3 hours. Separation of the solution was carried out using a buncher flannel with a single Wattman number 42 filter paper. Step 2. The extracted dye was then isolated from the ethanol solution by rotary evaporation and we obtained 8.5 gram of crude chlorophyll. Step 3. Coarse chlorophyll was added into petroleum ether until a yellow color appeared on column chromatography. Step 4. The separation process was continued by replacing the eluent with 10% solution of diethyl ether in petroleum ether to produce 0.76 gram chlorophyll or green color, 0.035 gram beta carotene or yellow color, 0.03 pyroceritrin or orange color, and residue. A detailed description of the scientist chlorophyll dyes can be found elsewhere. Step 5, or the last step, chlorophyll was dissolved in ethyl alcohol to obtain solution with various concentrations, start from 16, 17, 18, 19, and 100 millimoles. The synthetic dyes used in the study was 0.03 millimoles and N719 or diazole. The optical properties of dye were measured by UV spectroscopy. The functional group in these dyes were characterized by Fourier transform in infrared spectroscopy.
For the next slide is 2.2 DSSC fabrication and testing. For the number 1, fluorine doped tin oxide or FGO sigma Aldrich conductive glass was used as the substrate. The semiconductor was prepared by dissolving 0.24 gram of TO2 nanopowder or 21 nm sigma Aldrich into 4 ml of ethyl alcohol or 19.6% merc. For the number 2, TO2 paste was simmered on the FGO couch glass and flattened by the Dr. Black method until the TO2 film became a homogeneous layer. The semiconductor layer is minted at 20 meters and area of 1 centimeter square. For the next, number 3, then the TiO2 coat layer on the FGO substrate was sintered at 450 Celsius for 2.5 hours to improve the bond between the semiconductor and the FGO glass. For the next, number 4, after that the photoelectrodes were immersed in the dye solution for 24 hours each at 30 Celsius. For the last number is number 5. The opposing electrode is carried out by the spruting process. Catholic platinum was deposited on FGO glass in a vacuum tube at 9.5105 torr. The platinum target material is connected to the negative terminal at a high voltage of 404 voltage and 125 mA, while the FGO glass is connected to the positive terminal. The electrolyte solution was sintered by mixing 3.3 gram of sodium iodide or 99.95%, 523.875 mg of pure iodine or 99.95%, 5.481 gram of heteropolyzed or HPA, and 30 ml of acetonitrile. Iodine added in the electrolyte acts as an electron acceptor to prevent recombination and photoreduction of iodide. The electrolyte solution was injected into the assembled DSSC at 30 meters intervals and sealed with glass glue. The performance of the DSSC was determined by the solar simulator under 100 mW by centimeter square irradiation. The current voltage curve was measured with a digital multimeter to obtain SC, OK, FF, and DSSC efficiency.
Number 3. Results and discussion. Figure 1. The absorption spectrum in the visible light spectrum 400 until 700 nanometers for dye N719 and chlorophyll is shown in Figure 1. N719 has an absorption peak at 515 nanometers and chlorophyll has an absorption peak at 616 nanometers. The position of the absorption peak spectra was unaffected by variations in chlorophyll dye solution content, but the absorbance value at 616 nanometers was. This is consistent with the Lambert-Beard law, which states that a solution's absorbance is proportionate to its concentration along a light beam's same path length. And then we have figure 2 and table 1, which show the results of the cyclic voltammetry test for dye N719 and chlorophyll. The findings of the N719 and chlorophyll dicyclic voltammetry test are displayed in figure 2 and table 1. The energy level of the highest occupied molecular orbital, or HOMO, and the lowest unoccupied molecular orbital, or LUMO, were determined using the electrochemical oxidation and reduction onset potentials. The intersection of the tangents between the rising current and the baseline charging current of the CV curves was used to calculate the onset potential. The different amounts of a negligible impact on the LUMO and HOMO values of the chlorophyll dyes as indicated in table 1. And then we have figure 3, which shows the FTIR measurements of dye N719 and chlorophyll. The existence of the OH and CO groups respectively is indicated by peaks in the regions of 250 until 3000 and 1600 and 1750 centimeters on the power of -1 in all dyes. However, compared to chlorophyll dyes, the N719 dye produced more OH groups and CO scratching. In general, the CO scratching and OH groups were unaffected by the concentration fluctuation in chlorophyll dyes. And then figure 4 and table 2. Figure 4 and table 2 show the performance of the SSC based on the dye N719 and chlorophyll under 100 mW per centimeter square irradiation. All chlorophyll dye-based DSSCs have a lower energy conversion efficiency than N719 dye-based DSSCs. The N719 dye-based DSSCs had an efficiency of 1.293%, whereas the chlorophyll dye-based DSSCs had a maximum efficiency at 0.094% at 90 millimolar. And then last we have figure 5, which shows the increase of concentration of chlorophyll dye increase the efficiency of the SSC and can be seen from the increase in current density. The increase in current density is related to how much dye the titanium dioxide electrodes can absorb. However, the dye loading value increased while the effectiveness of the SSCs dropped at doses above 90 millimole. The precipitation of dyes on the titanium dioxide electrodes can be used to explain this outcome. This event gives rise to the possibility of some breakdown of titanium dioxide by the acidic carboxylic groups of the dye, the resultant of titanium plus ions combine with the chlorophyll dyes to create insoluble complexes, which precipitate in the pores of the film. On the titanium dioxide surface, this results in a formation of inactive dye molecules. Based on the results of this research, it has been determined that a concentration of 90 millimole chlorophyll dye interacts well with the titanium dioxide surfaces due to its high dye loading value without having a substantial negative impact on inactive dye precipitation.
For the last slide is about the conclusion of performance enhancement of dye-sensitized solar cells using a natural sensitizer is chlorophyll that has been extracted from papaya leaves can be used as a dye sensitizer in DSSCS. But for the level of energy conversion efficiency, the chlorophyll-based DSSC, the energy conversion efficiency is still lower than the dye-based DSSC synthesis. According to the data, DSSC based on dye N719 achieved an efficiency of 1.2 93%, while the highest efficiency for DSSC based on chlorophyll dye was 0.094% at 90 millimolar. The concentration of the dye solution also increases the efficiency of the DSSC due to an increase in the amount of dye absorbed by titanium dioxide. However, at concentration above 90 millimolar, the efficiency of DSSC decreases due to the selection of titanium dioxide nanostructure. This increases the amount of dye in the inactive molecules on the titanium dioxide surface and prevents the electron injection process in the DSSC. Meanwhile, variations in the concentration of chlorophyll solution didn't change the energy level of HOMO, LUMO, and COOH functionality.